In this lecture, you'll learn about the IP address classes. We're going to cover classes A, B, and C here, which are used for allocating addresses to our hosts. And then in the next lecture, we'll cover classes D and E. Okay, the first thing to talk about is the effect that that line has, which designates where the network portion of the address is and the host portion of the address. If a subnet mask is a /8, for example, using the first 8 bits for the network portion of the address, then 8 bits for the network portion, 24 bits for the host portion. If we compare that with a /24, we're going to have 24 bits for the network portion and only 8 bits for the host portion. So we could have a /8 is going to have not many networks, but a lot of hosts per network, or a /24 would have a lot of networks, but not many hosts per network. So we've got a trade-off whenever we decide where that line is going to be about how many networks we're going to have and how many hosts that we're going to have. Okay, let's talk about how internet addressing was originally supposed to work. Because when IPv4 was first conceived, the designers didn't know about what was going to happen with the internet. They didn't realize that there would be a huge explosion of usage and everybody would be using it and that everybody would require an IP address. So when they first designed it, they designed it for what was right at that time. And as we go through this section, you need to think about the internet, about how it was then, to understand why IPv4 was designed the way that it is. There's a few issues with IPv4 that you'll learn about as we're going through this section, and those issues came about because the designers didn't realize what was going to happen in future. So as long as you think about it from that point of view, then everything should make sense. So the original way that IPv4 addressing was meant to work, when a company wanted to communicate on the internet, they would apply for a range of IP addresses. Now, the global assignment of IP addresses is handled by IANA. That stands for the Internet Assigned Numbers Authority. So they are up at the top level looking at it from a global point of view. They assign large blocks of addresses to the local authorities in different regions. So a company, they would apply to their local authority to get a range of public IP addresses. If they had 6,000 hosts, for example, they would ask for a range of IP addresses big enough to cover that, plus some room for growth in the future as well. That company would then allocate those addresses to their hosts in their different offices. Unfortunately, when IPv4 was created, the designers didn't realize how big the internet was going to get, like we were just saying, so they didn't create a big enough address space. There's not enough IPv4 addresses for every host that actually needs an IPv4 address that's going to be communicating on the internet. So IPv4 ran out of addresses. The long-term solution for the problem is IPv6, which has got a much bigger address space. IPv4 is a 32-bit address, IPv6 is a 128-bit address, and we're going to be talking about IPv6 in a lot of detail in a later section. Private IP addresses with NAT, which is Network Address Translation, are, however, currently deployed in the majority of enterprise networks as a workaround. So IPv6 is the long-term solution, but today, private addresses with NAT is actually more commonly deployed. But as time goes on, there will be more uptake of IPv6. Again, we're going to discuss private addresses, NAT, and IPv6 in a lot more detail as we go through the course. But as I was saying, to understand the next few lectures, don't think about private addressing, NAT, and IPv6 yet. We're going to get to there later. To understand why we have those and how they work, you need to understand the original implementation first. So that's what we're going to cover first. So Class A addresses. The Internet authorities split the global IPv4 address space into separate classes. Class A addresses are assigned to networks with a very large number of hosts. So Class A, there's going to be a small network portion and a large host portion. The high order bit, which is the first bit in a Class A address, is always set to 0. And if you look down in the bottom left at the address there, you see I've highlighted the first bit. It's always going to be a 0 in a Class A address. With Class A addresses, the default subnet mask is a /8, so 255.0.0.0, and valid network addresses range from 1.0.0.0 to 126.0.0.0/8. So that's the network address. The actual host address ranges from 1.0.0.1 to 126.255.255.254. So 1 to 126, that allows for 126 networks. And if you counted up the host bits, 2 to the power of 24 adds up to 16,777,214 hosts per network. Now, you maybe noticed there, if you actually counted this up, the available values, if you set the first bit as 0, would actually be, we could have all zeros, and we could go up to 127. But all zeros and 127 are not in the valid address range that we can assign to our hosts because they are reserved addresses. 0.0.0.0/8 is reserved and signifies this network, and it's used by some protocols. So 0.0.0.1 to 0.255.255.255 are not valid addresses that you can assign to hosts. That entire range is not available. Also, 127.0.0.0/8, which is also in the Class A space, is also reserved. That is used as the loopback address, and it's used for testing the IP stack on the local computer. So 127.0.0.1 to 127.255.255.255 are not valid host addresses. So you see I've written down at the bottom here, whoops, they just wiped out over 33 million addresses that could have been used for addressing actual hosts on the public internet. If you think about it, this network, they could have just used a single address for that, like one address rather than 16 million addresses. And the same for the loopback, they didn't really need 16 million addresses to be used for loopback testing. And if you're thinking, well, there's this huge shortage of addresses on the internet, why would they do something crazy like that? But the reason is, when IPv4 was designed, they didn't realize that they were going to run out of addresses. So they thought, hey, it's no problem. We can assign 16 million addresses for testing. It doesn't matter because we don't have a shortage of addresses. They didn't realize what was going to happen later on. In fact, let me give you a demo of using the loopback. So let me open up a command prompt here on my laptop. And if I did an IP config, again, I've got loads of virtual adapters on here, but if I scroll up slowly, you'll see I don't have the IP address 127.0.0.1 assigned to any of my network cards in here. It's built in with IP. So I can ping 127.0.0.1, which is the loopback address, and you see I'm getting a reply, which means it's up. The reason you do this is to test that TCP IP is working on the local machine. If you wanted to check, say that you're in New York and you want to check that you've got connectivity to a server in Boston, you could ping that server. But there's not much point in pinging the server in Boston if you can't get to your local default gateway router in New York. So you would ping that first. And also, there's not much point in pinging the local router if TCP IP isn't even working on your laptop. So the way that you verify that TCP IP is up and running on your laptop is by pinging the loopback, and we can ping 127.0.0.1. But like I was just saying, it's the entire Class A range beginning with 127 that is actually reserved for testing loopback. So I don't have to ping 127.0.0.1. I could ping 127.100.200.50, and this is going to work as well. So I can ping anything beginning with 127, and it's going to check the local TCP IP stack. So it's good to have that address for testing, not so good that they took out an entire Class A network for it. Okay, so you see that all zeros would begin with 0, obviously, and 127 is 0 and then all ones. Class A always begins with a 0 as the first bit. Okay, now, obviously, a company that had a Class A address would not put all 16 million hosts into a single logical network. That would be terrible for performance and security. They would split that big /8 range up into smaller subnets and assign those to their different departments in their different offices. For example, if they received the Class A address 15.0.0.0/8, they could allocate the subnet 15.0.1.0/24 to sales computers in New York, 15.0.2.0 255.255.255.0 to accounting. That was just the same /24 in dotted decimal notation, and 15.0.9.0/24 to sales computers in Boston. So they would have that huge network that they got assigned by the internet authorities, and they would split it up into smaller subnets that they could assign to their different offices and their different types of hosts in different offices. And when you do that, it's called subnetting. You're going to master subnetting in a later lecture because it's super important.